This ongoing research studies the effect of sunlight on ambient temperatures inside conduits above rooftops. It was started for the purpose of creating a database of information that can be used by electricians, designers, and inspectors to accurately apply the provisions of NEC Table 310.16. In our first study of rooftop conduits, we built this building and we installed 19 various conduits above the roof. We saw a 30 degrees centigrade increase above the outdoor temperature. In the earlier experiment, there was some question as to whether we had covered all of the bases. So we built these simulated black and white roofs, and we mounted at various elevations conduits and cables on the roof at 5/8, 1.5 inches, 3.5 inches, 6 inches, 12 inches, and even 36 inches above the roof, so that we could determine what the various differences in temperature would be. We also measured the air inside conduits. None of these conduits, cables, were connected to a source or power supply, so they're unloaded. This means that the benign outdoor temperature is the only thing we're measuring. This little device is a temperature sensor. It's actually made of copper and copper tin wire fastened at the ends. They call it a thermocouple. This happens to be a type T thermocouple, and the temperature range is in the ambient ranges. It goes well below and well above any temperatures that we're going to examine here. These sensors are attached to the insulation of the conductor inside the conduit. Some of them are floating through a sponge so that they can sense only the air inside the conduit. This gives us some certainty of the values that we'll be obtaining and the data that we'll be obtaining from the research. We also have thermocouples in the roof surface so that we can measure the temperature of the roof itself between the underlayment material and the mineral rolled roofing. We have sensors that are in an outdoor aspirated enclosure that show the outdoor temperature. We also obtain wind speed. We have a pyranometer, which gives us the intensity of the sun. We have temperature sensors on the bottoms, inside the conduit, on top inside the conduit. From all of this, we then route the sensors underground into our control room. For the data collection, we use a Campbell Scientific CR5000 data logger. It is connected to a device called the thermocouple multiplexer. We have 12 of those in this room. Each one of those allows 25 channels of thermocouples to be attached to the data logger. The data logger is then connected to the computer, and the computer can then collect from the data logger data periodically as it is programmed. 8 years of research has shown that the ambient temperature inside conduits on rooftops in sunlight is consistently higher than the outdoor temperature. We also now know that the elevation of a conduit above the roof is the primary factor that causes the difference between the outdoor temperature and the ambient temperature inside the conduit when exposed to sunlight. The higher the conduit is above the roof, the less the ambient temperature inside the conduit rises above the outdoor temperature. A conduit in direct sunlight that is between 0 and 1/2 inch above the rooftop should be adjusted based on a temperature of 60 degrees Fahrenheit or 30 degrees Celsius above the outdoor temperature. A conduit in direct sunlight that is between 1/2 and 3.5 inches above a rooftop should be adjusted based on a temperature rise of 40 degrees Fahrenheit or 22 degrees Celsius above the outdoor temperature. A conduit in direct sunlight that is between 3.5 and 12 inches above the rooftop should be adjusted based on a temperature rise of 30 degrees Fahrenheit or 17 degrees Celsius above the outdoor temperature. A conduit in direct sunlight that is between 12 and 36 inches above a rooftop should be adjusted based on a temperature rise of 25 degrees Fahrenheit or 14 degrees Celsius above the outdoor temperature. With these data, we now have a proper way to apply the correction factors of NEC Table 310.16.